Hey everyone, my name is Taylor Sparks. I'm the editor-in-chief of Integrating Materials and Manufacturing Innovation. And I have a paper to talk about today, and uniquely, this one actually comes from my own group here at the University of Utah. It's entitled Revolutionizing Scientific Figure Decoding, Benchmarking LLM Data Extraction Performance. Now, first off, I want to point out that even though I'm editor-in-chief of this journal, I don't handle, obviously, any of my own submissions. And all my papers are handled by guest editors. This one was handled by Ankit Agrawal at Northwestern University, so thanks to him to overseeing the editorial process for my own submission. Second thing I want to point out is that this came from contributions from Ivan Turan. He was the lead author, which is a high school student here in Salt Lake City. So this is work between him and I. Now, what we were interested in is this notion of language models being able to extract data from figures. There's been a lot of attention paid towards language models pulling data out of text. And honestly, that is becoming a very robust field. It's essentially becoming a solved problem, in my opinion. But getting data out of the figures, that is a totally different question. And that's where we've really struggled in the past. Now, there is a little bit of prior art in the literature. For example, there's this paper by Pollock and Morgan, which is just a preprint right now, where they've tried to look at multimodal models for getting data out of plots. Now, what they focus on is data extraction from what I consider simple two-axis plots. They're focusing on high precision. They're getting upwards of 90% in point identification and value estimation. But again, they're looking at relatively simple plots. You can see their paper here. Here's the archive paper. I don't know if it's fully published yet. But this work was essentially submitted about the same time as ours as well. Other than that, I haven't seen much done before. So we decided to go beyond what we saw in that work, and we decided to extend it to looking at a more comprehensive list of the types of figures that you see in material science. And we decided to compare it with some state-of-the-art multimodal language models, GPT-4o, Perplexity Sonar, and Gemini 2.5 Pro. Here's the figure that really inspired the work. Somebody told me that language models, the sort of ChatGPT type tools that we're using all the time now, are actually good enough to start getting data out of figures. I was pretty skeptical, and so I took this XPS data, I went ahead and did a manual extraction with WebPlot Digitizer, and then I passed the figure to the language model and just asked it to do the extraction. I didn't tell it what the axes were, I didn't do any of the alignment things that you do with manual annotation, and I was blown away at what I saw. Here you see the results. You can see that while the manual annotation in the middle, the green data points, are the most correct, the other two data points are honestly not that bad. The fact that it was even getting the rough general trend was remarkable. Now, there are some problems. It's shifted by about 2 EV, which is a big deal if you're doing XPS. The baseline shift. But the fact that it's even getting it close had us asking the question, how good, where are we at in this field? This was a relatively simple plot. How does it do on more complex plots? So we set out to explore the performance. We did so on 9 diverse different plot types. You can see all the figures that we did the extractions from in the supplemental information, but here this table 1 sort of summarizes, right? Single experiment line graphs, single experiment scatter plots, multiple color representation graphs, multi-panel plots, 3D plots, heat maps, bar charts, isopleth or contour plots, and schematics and diagrams. You can see lots of examples. I've put a few of them in here. Multi-panel plots, here's an isoplethal, right? In terms of how well it does, we looked at 3 different evaluation metrics. One is, did it get the right number of points? That's the percent point error, right? If there were 10 data points in the original figure and it extracts 8, then there's some error associated with that, right? The other thing we asked for was the X accuracy and the Y accuracy. Did it get the point in the correct X position? And we get it in the correct Y position. Now, if it didn't have the same number of points, then we wouldn't be able to do the X accuracy and Y accuracy assessment, because you technically need to do a point-by-point comparison. The way that we got around that is it says here, if the number of points in the replicated plot didn't match the original plot, then we would use curve fitting, since a direct comparison wouldn't be possible. Once we were able to fit the curve to the replicated plot, then we would use the fitted curve to predict the X and the Y locations from that, right? I encourage you to take a look at the paper and just see some of these images, right? On the left top here, you see the original image. On the right top, you see the GPT-4o reconstruction. And then we can actually create a generated data versus original data plot to see how well it's doing. And in the more complex plots, look at this. This is pretty bad. It's actually not doing a very good job at all. While the simple ones, it tends to do significantly better. Here's an example showing you the original in a multi series data set graph with different colors, and then the extraction. again, the correct trends and the rough orders of magnitudes are all correct. The exact values do have some problems. The exact number of points are also incorrect. So what are some of the takeaways? I am convinced after doing this study that there is an exciting opportunity for multimodal data extraction from figures. I had considered computer vision for data extraction from figures to be a long ways off. I've changed my mind. I think it's actually closer. We've seen, again, with this current fleet of models, which are generalist models, they were not fine-tuned for data extraction from figures, but even they are able to do some degree of reliable data extraction from relatively simple plots, things like single experiment or scatter graphs, but they do begin to struggle with the more complex representations, 3D multi-panel isoplethal graphs. Another thing that we observed is that GPT-4o did consistently outperform the other multimodal language models that we attempted. And clearly one of the takeaways is that there is room for additional research in this field. Obviously, with fine-tuned models that have been trained specifically on data extraction from figure tasks, I think we're going to see some big jumps in improvement. So it's an exciting time to be in this, and I hope you'll read all about this paper in the latest issue of IMMI.